Today we will discuss a result in functional analysis. Remark: if X is not a Banach space, Y is a Banach space, then open mapping theorem fails. Then open mapping theorem fails. Example: consider an infinite dimensional space infinite dimensional separable Banach space Y. For example, we can take Y equal to little lp for some p with 1 less than or equal to p less than infinity. Let set Ys such that S element of S be a Hamel basis for Y with the norm Ys equal to 1 for all S in S, for all S element of S. Then by 8.4 S is an uncountable set. Let X denote the set of all scalar valued function functions on S. Which vanishes at all but finite number of elements of S. Then X is a linear space over K. And clearly X is a linear space. Over K. Under point-wise addition and scalar multiplication. For X in X, let norm X equal to summation over S in S mod X of S. then norm is a norm on X. Note that X is not separable. Since for a fixed S in S, let excess of t is equal to delta st for t element of S. Then set of all x's such that S element of S is an uncountable set in X. And norm xs1 minus xs2 equal to 2 whenever s1 not equal to s2. This is because norm xs1 minus xs2 is actually summation over t in S mod xs1 of t minus xs2 of t. That is equal to summation over t in S mod delta st minus delta s1t minus delta s2t. This is because xs1 of t is delta s1t and xs2t is delta s2t. But we have delta st equal to 1 if s equal to t and it is 0 when s not equal to t. So this is actually modulus of delta s1 s1 minus delta s2 s1 plus mod delta s1 s2 minus delta s2 s1 s2 s2. So this is actually mod 1 plus mod minus 1. This is because we have delta s1 s1 is 1 and delta s2 s1 is 0. So this is actually mod 1 and delta s1 s2 is 0 and delta s2 s2 is 1. So this is actually mod minus 1. So this is equal to 1 plus 1, that is equal to 2. Therefore X is not separable. For X in X, define f of x equal to summation over s in S x of s into ys. Then clearly f from x to y is a linear map. and f is continuous. We will prove the continuity of f, that is f is continuous since norm f of x equal to norm summation over s in s x of s into ys. This is actually x of s into y of s. Okay, this is actually x of s into y of s. So this is norm summation s in s x of s into y of s. But this is less than or equal to, this is less than or equal to summation over s in s mod x of s into norm y of s. And this is actually summation over s in s mod x of s, because we have norm y of s equal to 1 for all s in s. So this is actually norm x by the definition. That is norm f of x is less than or equal to norm x for all x in x. Therefore f is continuous. And being continuous, f is closed. Also f is bijective. And f is not an open map. We will prove this. If f is an open map, then for E open in X, we have f of E is open in Y, which implies f inverse from range of f to X is continuous. Since for open set E in X, f inverse of E equal to, this is actually f of E is open in range of f. That is, if f is open, then f from x to y is continuous. And f inverse from range of f to x is also continuous. Which implies f is a homeomorphism. That is, f from x to y is a homeomorphism. that is F is a homeomorphism from a non-separable normed space X to a separable normed space Y which is not possible. That is, here F from X to Y is a homeomorphism where X is a non-separable normed space and Y is a separable normed space. So, which is not possible. Therefore, F is not an open map. That is, we have F from X to Y where Y is a Banach space is closed and surjective but F is not open. This in fact implies that X is not a Banach space. Therefore, we can say that if X is not a Banach space and Y is a Banach space, then open mapping theorem fails. We can use the same example to prove that a closed graph theorem fails if X is not a Banach space. So here, since F from X to Y is closed, since F from X to Y is closed and bijective, F inverse from Y to X is also a closed map. However, F inverse is not continuous. Since F is not an open map. If F inverse is continuous, for open set E in X, F inverse of E is open in Y, implies F of E is open in Y, which is not possible. Since F is since F is an open map. Since F is an open map. That is F inverse from y to x is a closed linear map, but F inverse is not continuous. Therefore, even though Y is a Banach space, closed graph theorem fails if X is not a Banach space. Even though Y is a Banach space, closed graph theorem fails if X is not a Banach space. That is, the closed graph theorem fails if the range space is not complete. Although the domain space is complete.